In last video, we discussed about what are oxyacids, their physical trends in the properties, trends in physical properties like thermal stability or their acidic nature, as an oxidizing agent. And at the end of that video, we discussed about the structures of oxyacids on the basis of valence shell electron pair repulsion theory. And you know there are 4 steps to find out the structure of oxyacid. Step 1 is draw the Lewis dot structure, find out total number of bonding pairs or bond pairs of electrons and lone pairs of electrons. Then find out the steric number, and steric number, it is the sum of number of atoms attached to central atom, that is number of bond pairs plus number of lone pairs. And last step is considering total number of bond pairs and lone pairs, or considering the steric number, draw the structure for the oxyacid. So these are the 4 steps. Now in this video we are going to discuss the structures of some of the oxyacids of chlorine, of what is the steric number and what is the correlation between steric number and hybridization of the central atom. So central atom undergoes hybridization. It can be sp3, sp3d, sp3d2, and when hybridization is sp3, then the geometry of that particular molecule will be tetrahedral. Or if central atom undergoes hybridization sp3d, then its geometry will be triangular bipyramidal, and so on. So by knowing hybridization of central atom, it is possible to know the structure or geometry of the molecule, that is oxyacid of the chlorine. And there is a correlation between steric number and hybridization of the central atom, and the formula is H is equal to half V plus M minus C plus A. Now what is H? H is number of hybrid orbitals, that is steric number, and it is equal to number of bond pairs plus lone pairs. What is V? V is a number of valence electrons of the central atom. In oxyacids of chlorine, chlorine is the central atom. In outermost shell of chlorine there are 7 electrons, so value of V is 7. Now what is M? M is monovalent atoms attached to central atom. So in oxyacids of chlorine, chlorine is the central atom and it is attached to oxygen. Okay, so oxygen is not a monovalent atom. So M is a monovalent atoms attached to central atom. What is C? C is a number of positive charges on cation. C stands for cation. If there is a 1 positive charge, then value of C will be 1. If 2 positive charges are there, C is equal to 2. Now what is A? A stands for number of negative charges carried by the anion, and for any particular anion with 1 negative charge, value of A is equal to 1. When 2 negative charges are there, A is equal to 2. Now look at this table. Now depending upon value of H, we can know the geometry of molecule. So when value of H is equal to 2, it is nothing but steric number also. When steric number or H is equal to 2, central atom undergoes sp hybridization and expected geometry is linear. When H is equal to 3 or steric number is 3, central atom undergoes sp2 hybridization and resulting geometry will be triangular. If H is equal to 4 or steric number is 4, central atom undergoes sp3 hybridization and geometry of molecule will be tetrahedral. If steric number is 5 or H is equal to 5, hybridization of central atom will be sp3d and expected geometry will be triangular bipyramidal. If H is equal to 6, then hybridization of central atom will be sp3d2, geometry of molecule will be octahedral. Similarly, when H is equal to 7 or steric number is 7, then central atom undergoes sp3d3 hybridization and expected geometry will be pentagonal bipyramidal. I will take example, that is structure of hypochlorite ion. In hypochlorite ion, there is a one chlorine and one oxygen. Electronic configuration of chlorine is atomic number 17, 1s2, 2s2, 2p6, 3s2, 3p5. Outer electronic configuration for chlorine, it will be 3s2, 3p5. Total 7 electrons present in outermost shell. For oxygen, atomic number is 8, configuration is 1s2, 2s2, 2p4. Valence shell electronic configuration for oxygen is 2s2, 2p4 and 6 electrons present in outermost shell of oxygen. Now, knowing the number of electrons present in outermost shell, one can draw the Lewis dot structure for ClO- ion, that is hypochlorite ion, and this is the Lewis dot structure. In between chlorine and oxygen there is one bonding pair, so there is a single bond between chlorine and oxygen, and there are 3 lone pairs at chlorine, 1, 2, 3, and therefore number of bonding pairs equal to 1, number of lone pairs at chlorine equal to 3, and steric number will be 1 plus 3, that is bond pairs plus lone pairs, that is equal to 4. Steric number is 4, and therefore this is ABE3 type of molecule. E stands for lone pairs. There are 3 lone pairs, and therefore the expected geometry is tetrahedral, with chlorine is at the center of tetrahedron, and out of 4 corners of tetrahedron, 1 corner is occupied by oxygen. There is only 1 oxygen, whereas 3 corners, these will be occupied by the lone pairs of electrons, and lone pair repulsion is highest. And actually observed geometry for hypochlorite ion is a linear. Now alternative method is H is equal to half V plus M minus C plus A. V is valence shell electrons of central atom, that is chlorine. M is number of monovalent atoms, C is positive charges, A is negative charges. Knowing these values, so for chlorine number of valence electrons are 7, and it is an anion and it carries unit negative charge, and therefore value of A is 1. So 7 plus 1, that is 8 by 2, that is equal to 4. If H is equal to 4, then hybridization will be sp3, and there is a 1 bond, and therefore bonding pair equal to 1 and lone pair is equal to 3. So this is the alternative method. Another example, structure of chlorite ion, that is ClO2 minus. This is the Lewis dot structure. Chlorine is attached to 2 oxygen atoms, so there are 2 bonding pairs for chlorine. This is 1 and this is 2nd. Similarly, there are 2 lone pairs or non-bonding pairs, and therefore number of bonding pairs equal to 2, number of lone pairs equal to 2, and steric number, that is number of bond pairs plus lone pairs, that is 2 plus 2, that is equal to 4. But here this is AB2E2 type of molecule because there are 2 lone pairs. Okay, expected geometry is tetrahedral, but there are 2 oxygen atoms and 2 lone pairs. Chlorine will be at the center of tetrahedron, 2 corners of tetrahedron it will be occupied by the oxygen, and rest of the 2 corners occupied by the lone pairs. And because of greater lone pair repulsion, the chlorite ion, this is angular, okay, and not linear. Observed geometry is angular, but expected geometry is tetrahedral because steric factor is 4. Now alternate method is H is equal to half V plus M minus C plus A. Now alternate method is very simple. There is no need to know about the Lewis dot structure. Just by knowing number of valence electrons of chlorine, number of monovalent atoms attached to chlorine, and charges, positive and negative charges carried by the anion, we can find out the steric number, even number of bond pairs and lone pairs. So this is the formula. Valence electrons are 7, negative charge is again 1, so 7 plus 0 minus 0 plus 1, that is 8 by 2, again it is equal to 4. So this chlorine undergoes sp3 hybridization. Total number of bond pairs are 2. Why 2? Because chlorine is attached to 2 oxygen atoms. So bond pairs are 2. And there must be 2 lone pairs, because bond pair plus lone pair, this must be equal to 4. And therefore lone pairs must be 2. So there are 2 lone pairs and 2 bond pairs. And this is the geometry, that is angular. Now third example, that is structure of chlorate ion, ClO3 minus. Lewis dot structure. Chlorine is attached to 3 oxygen atoms and there are 3 bonding pairs and there is a 1 lone pair at chlorine. So total number of bonding pairs are 3, lone pairs equal to 1, steric number equal to bonding pairs plus lone pair, that is 3 plus 1, it is equal to 4. But this is AB3E type of molecule, there is 1 lone pair, and therefore expected geometry is again tetrahedral, but observed geometry is trigonal pyramidal, where chlorine is at the center of tetrahedron, 3 corners occupied by the oxygen and 1 top corner it is occupied by the lone pair, and therefore molecule looks like a trigonal pyramidal. Okay, alternative method again, H is equal to half V plus M minus C plus A, it is equal to half. Now number of valence electrons at chlorine again 7, monovalent atoms 0, positive charges 0, negative charges 1. So H is equal to 4 means steric factor is 4, but here chlorine is attached to 3 oxygen atoms, so bond pairs equal to 3 and therefore lone pair must be equal to 1. This is the alternative method, and in this way chlorate ion has a geometry of trigonal pyramidal. Now the structure of perchlorate ion, that is ClO4 minus ion. So here Lewis dot structure is, so Cl it is attached to 4 oxygen atoms and each chlorine it is attached to oxygen atom and there are 4 bonding pairs. Now here one of the oxygen it carries negative charge, and here total number of bond pairs are 1, 2, 3, 4 and lone pair is 0. So number of bonding pairs equal to 4 and number of lone pairs equal to 0. Okay, steric number, this is equal to 4 plus 0, that is bond plus pair plus lone pair, that is equal to 4. This is AB4 type of molecule, lone pairs are absent and therefore this molecule has a regular tetrahedral geometry. So expected and observed geometry is same, that is tetrahedral, where chlorine is at the center of tetrahedron and 4 corners of tetrahedron are occupied by the 4 oxygen atoms. This is the alternative method. H is equal to half V plus M minus C plus A. Again valence electrons of chlorine equal to 7, anion negative charge is equal to 1, so H is equal to 4. Bonding pairs are 4, lone pairs are 0. Now summary of this point is, summary of structures of oxyacids. The hypohalite or hypochlorite ion has a linear structure. Then chlorite ion has an angular structure. Then chloric ion has a trigonal pyramidal structure, or OX3 minus ion has a trigonal pyramidal structure, and perchloric ion has a tetrahedral structure where halogen is at the center and 4 corners occupied by the oxygen atom. So this is about the structures of oxyacids of the chlorine. In next video we are going to discuss the interhalogen compounds.